Hello, my name is Will Gutekunst. I'm an associate professor here at Georgia Tech in the School of Chemistry and Biochemistry. And I also have a courtesy appointment in materials science and engineering. So my group is a synthetic polymer research group. So we're effectively interested in making polymers of different types. So if you're unfamiliar, polymers are really long strings of molecules made up of things called monomers. Most people associate these with things like plastics, but you can also have these identified in like more biochemical areas like DNA or proteins. So we are on the synthetic polymer side of things, and I really think polymers are interesting because you can take these small molecules, these monomers, they could be a liquid, they could be a gas, and we start to connect them all together, you get these emerging new material properties. And these molecules can be, ginormous, they can be hundreds of kilodaltons in molar mass, and really you can have a lot of flexibility in how you're making them, what material properties they're going to have based off of the monomers you design. So we're really at the sort of synthetic organic side of things. We like to develop new monomers. We like to see how these monomers can polymerize to develop new types of materials to, ask either basic science questions and also address really key issues in the field. So if you think about plastics, there's like this stigma associated with them. We're trying to address some of this. We're trying to find new ways towards polymer recyclability, ways to enhance sustainability, and really try to learn something new about the chemistry along the way. So in a project in my group, we use all sorts of different types of techniques. So at the beginning of a project, it's really like synthetic organic chemistry. We're making monomers, and then we're doing reactions to turn those monomers into polymers. So this involves sort of your traditional, you're working in a fume hood, you're using Schlenk technique to keep all the air out, keep things dry. We're isolating the polymers and monomers through standard chromatography techniques or precipitation. And then comes sort of the characterization of all these things we just made. So that can be solution NMR to make sure that the structures are correct, to make sure that the polymerization worked as we anticipated. And then this will transfer then to try to figure out how big is this polymer. So we'll use things like size exclusion chromatography to get an estimate of its molecular weight. And then we're gonna go into studying its sort of basic thermal properties. So these are measurements like differential scanning calorimetry to see if there's a glass transition temperature or if there's any melting or freezing transitions in the material. And also do things like thermogravimetric analysis to see how thermally stable these new polymers are. And then after this, we will do a variety of other additional characterization techniques depending on what the project is. So in some cases, my students will do this. Sometimes we'll do this in collaboration with others. This could be anything from rheology to AFM to tensile testing. Really, a whole lot of techniques can kind of come into play. And more recently, we've also been using a lot of computational chemistry to kind of augment our synthetic chemistry and wet chemistry needs. This comes from either DFT to try to determine the strain of a new monomer we want to make, going all the way towards a number of collaborations we have now with people in the machine learning and artificial intelligence areas to try to inform the chemistry that we want to do before we do it to make sure we're going in the right direction. And so getting to what these projects actually sort of involve, we have a lot of projects. I have maybe a short attention span. I like a lot of different things. And anywhere there's, I think, a synthetic challenge at place, then I'm generally interested in what we can do in that area. So from a theme that has kind of emerged in our group that is topical right now is in polymer sustainability. So a lot of plastics that people are making currently, we use every day, these are persistent materials. We don't really have a great way to recycle them. A lot of them are going into landfills, and we really need to have better answers to address this pressing challenge. And what we are doing in my group, we're trying to approach this problem in a few different ways. One way is to take sort of a traditional material, something that everybody knows and loves, and we introduce methods, new molecules that we can introduce into the polymerization, and it'll put weak links into the polymer backbone. This will let us then take this material, has the same properties of the things you know and love, your styrofoams, your polyethylenes, but now we can actually break them down with external stimuli. This could be chemical, it could be light, or different means like that. In another venue, we're trying to develop entirely new types of materials. So these are monomers, and where you can polymerize them, make a polymer, it can do its job, and then on demand, it will depolymerize and go all the way back to the monomer we originally started with. So this is a really effective strategy because whenever you normally take a plastic and you go through like the mechanical recycling process, you erode its material properties. It's not as good the second time you use it as the first time. With this, we're going all the way back to the original monomer. This means we can completely resynthesize the material. We don't have these loss in in mechanical or material properties, and also gives us a way to maybe re-engineer things again with different properties from its original purpose. So really it gives a lot more options, and also brings us back away from this sort of landfill problem that is kind of everywhere. In other projects, we do things that are kind of wild. We have a project right now in trying to turn polymers, so soft materials, and turn them into ceramics. So these are polymers that whenever you sinter them, so think about like taking clay and putting it into a kiln and turning it into a ceramic, you can do the exact same thing with these soft polymers, and they turn into now high performance, new high performance hard materials. The advantage of this is we can shape them and mold them beforehand, and we're even working on ways we can do 3D printing of these structures before we go and sinter them to the final ceramic product. In other instances, we're interested in developing some proton-conducting membranes with sequence-defined polymers, where our chemistry is really integral in precisely putting these charged functional groups in specific places in the polymer backbone. And also just asking like kind of some basic science questions. So weird molecules like fluxional molecules, this thing called bovaline, it will isomerize into all these different microstates. It's kind of like a ball and socket. And when we just wanted to ask the question, what does this do if you put it into a polymer, or things like liquid crystals? And we have secured funding to actively explore and try to answer these types of questions. As far as people in my group, so I really like to try to mentor students in a fairly active fashion. I don't like to lose contact with people too much. I try to stay involved. I try to keep up with the science, try to figure out what pitfalls are there, what new discoveries we found. I meet with people on a weekly basis, either individually or in subgroups. I'm not actually like in the lab anymore that much. I'm not like doing the science, but I try to go in there, see what's going on and try to still keep in contact. And through this, the sort of makeup of my group, and I think this kind of pertains to how the group is styled, we have people with a lot of different backgrounds. We have people with a lot of different research interests. Some people in my group, and they're all about the organic reactivity, really what reactions we're doing, how you can innovate on this end. Other people, they're like, that is a tool for me to get to try to address the problems that we're trying to solve with these polymer materials. And they may be more interested in the characterization and studying the material after they make it. And having these two sort of types of people together in one group, this lets us kind of use everybody's strengths to their advantage, right? One person could be making something, another person can kind of come in and do the characterization, or one person can do it all. It's sort of a choose your own adventure game in that respect. And I think this opens up opportunities to really let people shine in sort of the directions they want to take their own research, while still overall, keeping the same mission that I have for the group and sort of our overall research directions. Another thing that I always, I think, really impress on students is that, becoming a quality scientist is always going to be part of the PhD. But the other thing that I really want people to take away from my group is becoming an effective communicator of science. So this involves essentially giving good presentations. Can you describe your science to somebody at any given level, really? And so this is something we really actively work on in the group. So in our group meetings, we regularly will have presentations for any upcoming external talk that someone in the group is doing. We will go over slides, we will look at color schemes, we will look at layout, we will look at someone's delivery, and we'll look at the overall message. And we'll really dissect it afterwards and go slide by slide to try to give constructive feedback on what people can do better. Because if you are up there giving a talk and you're uncomfortable, there's some techniques you can do to make sure that your message will still be heard loud and clear, and you won't leave anyone in the audience behind. And I think this will translate to any career path you choose in the future, and really become a life skill that will help you along the way. My group is also on campus is really involved in a variety of different student groups. I've always encouraged people to go and sort of explore these different activities. We've had several members of the group become part of the leadership in the Student Polymer Network, in the Graduate Student Forum, in Women in Chemistry, and really become members of these different societies and groups. I think through these groups, you're able to perform outreach. You can generate new social circles, and you can also engage with industry and organize symposia, invite speakers in, and I think it really augments the classical graduate student experience by really making you a more well-rounded scientist. You can learn about what other people are doing more. You see what's going on in the real world a bit more. And I think this overall really builds up people overall, so that you're not just only focused on science, you're looking towards making yourself more marketable towards your next career in the future. And Georgia Tech, I think, is just a wonderful place to do science in general. We have people in our school who are doing, science in all different areas, from, origins of life research to, working on different problems. But I think the real strength of Georgia Tech for a grad student is really the interdisciplinary nature of the institute as a whole. So the barriers for collaboration are super low. I can pretty much knock on anyone's door, and if we want to start a project together, we want to work on something, there's no barriers getting in our way. And this goes all the way down to the student level. I've had grad students who come to me and they meet somebody through maybe one of these student organizations, and they come up with a project that they want to do, and they see how their two research interests can align and how they can do something really interesting together. And through these barriers, like, I don't even need to know how to do half of this stuff, because our instrumentation on campus and our characterization facilities are so strong. We have people that are full-time staff. You can go and just talk to someone. It's like, I want to learn how to do AFM. You will be trained. They will help you to interpret your data, and then you can become a functioning scientist in this technique and be proficient so you can actually apply it to your research. And I think that's an opportunity that not a lot of other places have, and it really empowers the student to go and check out new lines of research, new lines of inquiry, and do things that I never learned how to do. And I think that's really amazing for a research group.